Hello and welcome to the video directions for our lab here, which is the simulation of two-dimensional collisions using this website, which the link for was included in the lab handout. Okay, so I just want to go over how to get started and what the 6 different type of collisions we're looking at could, for example, be set up as. I also want to show you what I clearly mean by the 3 final conditions. Because that's how we're going to get our 18 different sets of data. So when you first navigate to the page, you're going to get dropped off here on the introduction type of collision. This is for really simple head-on collisions, but that's not what we're doing because we are doing two-dimensional collisions. So we go right over to advanced. All right, so let's just look in depth here at procedure 1, because this is going to be very similar to all the next ones. And if you haven't noticed already, this lab is really about just kind of running a series of simulations. There's not much in the way of follow-up questions. It's mostly just running the simulations and doing the calculations to back up your confidence in those simulations, or at least get practice with the numbers. Okay, all right, so there's 6 different versions. The 6 different versions are all going to be about how we orient these balls, how we change their velocity vectors, and so on. Okay? Alright, so let's look at number 1. So first of all, it's going to be 2 dimensions, which it is as soon as we went to the Advanced tab. Then we're going to turn on all the other boxes. So check, 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 and check. Okay? We're going to leave elasticity at 100%. We're going to make sure mass 1 is less than mass 2, which it already is. Then we're going to slow down the sim speed to about 1/4. The default is half. Okay, so get that on 1/4. Okay, and there. Sometimes the kinetic energy, you have to turn it on and off twice. See how it, yeah, so I've noticed that, and you saw I just did that. So if your kinetic energy isn't showing up here in the lower left hand corner, just turn the box off and back on to get it to show up. Alright, it's a word of warning there. So now, right, experimental procedure number 1. And you'll kind of get used to the wording, but I'm going to go through each one of them. So align the initial velocity vectors so that they exactly face each other along the x-axis and are anti-parallel to each other. Align the center of mass of the system so that it does not align with the geometric centers of either ball. If the center of mass of the system had aligned with both the geometric centers of the balls, then this would actually be a 1D collision, and we'd be doing it on the introductory tab. So since the lab and the tab correspond to 2-dimensional collisions, it doesn't make sense to do a system where they're hitting head-on and they're lined up. Okay, so how do we make sure they hit head-on? Well, unless you want to change the masses of the ball, you don't want to leave this dialog box in this mode. Instead, you want to click on the More Data button here, which opens up a lot of useful information. It has the masses, it has the positions of the center of masses of the ball, of both balls individually. It has the initial velocities of both balls. In fact, it'll be instantaneous because this data will be changing as the balls move when we run the simulation. Okay, as will the position data for that matter. It does not have the center mass of the system, but you need only make sure that the 2 centers are not identical lined along or do have identical y values, and then you will know that your center of mass is not aligned with either. Okay, and I'll show you what I mean in just a minute. So let's go ahead and get these somewhere like this, and what I'm going to focus on right now is their velocities. Okay, so I can move the velocity around and notice how the numbers change. Alright, I'll notice also how the momenta vector change. That's something you're going to be drawing, but right now we care about the velocity component. Specifically, I'm looking at the y velocity component, because the x velocity component only really matters for getting the 3 different final states that you're asked for. Okay, more on that in a minute. But here, if I put it, see I can't get it on 0. See that? It's on 0.007, and then it's on, I can get it to negative 0.07, 007 that is, but I can't get anything in between. That just has to do with your computer and the way you loaded it and the size of your window. Okay, so the fact of the matter is that that's fine that it's not quite at 0, because I can just line the other one up to that same value. Okay, so I'm going to go to positive 0.07. Now I know that these 2 balls have velocity vectors that are exactly anti-parallel, thereby meeting the condition that was asked for in procedure 1. Okay. Now, what about this thing about the aligning their center of masses so that they're not aligned at the geometric center of either ball? Well, all I have to make sure is that the two balls have different y values. And you can visually confirm, if you look, there's the x for the center of mass. The number 1 is at the center of mass of the red ball, and the number 2 is at the center of mass of the green ball. Those three figures, the x and the two numbers, are not in a line, right? Some are higher and lower. Okay, the center mass is closer to the being aligned with the bigger ball, but it's not quite aligned with the bigger ball either. And besides that visual confirmation, you just look at the numbers and make sure that they have different y values. And indeed, ball 1 has a y value of 0.021, and ball 2 has a y value of 0.061. They're not the same. Okay? All right, so then it's just a matter of running the simulation. There we go. Okay, so what happened there? Okay, so the two balls bounced into each other, and it kind of looked like one went straight up and the other went back the way it was going. So we need 3 different things to happen. So if you scroll down, it says that for each of the 6 types of two-dimensional skewed head-on collisions described in the procedure, do the following. Adjust the initial velocity magnitudes until 3 different final results are achieved. And I say the velocity magnitudes, but you can also adjust the masses here. I want to be clear on that. I should probably change the wording and say the initial momentum magnitudes until the 3 different final results are achieved. Okay? But you're absolutely allowed to change the masses to get these 3 final results. I only care that you get these 3 different final results. Result 1, both balls bounce back in the direction they came from. Final state 2, both balls travel to the left after the collision. Okay? And then final state 3, both balls travel to the right after the collision. So this state kind of isn't any of them because one of the balls is heading directly up. So let's reset things and adjust our mass. All right, so let's go to less data, and I just want to make the ball here more massive. Okay, let's make it actually slightly less massive. There. Okay, so instead of 1.5, we made it 1.3. Let's run it. Okay, that clearly worked. Got more data retroactively, but clearly we can see after the collision both balls bounced back in the direction they were heading. So the green ball turned around, not completely, it doesn't have to turn around completely, but it just has to go back in that direction, have a component in that direction. Right? So the green ball is going back towards the right, and the red ball is going back towards the left, the directions they came from. Okay? But if we want them both to head towards the left after the collision, I can go ahead and just make the green ball really massive. All right, let's reset things. I could also make the velocity faster. Okay, so I could have, let's just show you. Okay, so I could leave it at 1.5, the original mass, and just make the velocity really big. But I have to make sure I'm lining it up to 0.007 again, which would take me going to the more data menu, which I guess I'll go ahead and do. Okay, so not quite. That one seems, yeah, that one's too low. See, you can't really tell until you check here. Okay, let's get it. Because that's the downside I'm missing with it. See how it changed the values that are achievable now? But that's fine because you can see as long as you adjust both of them, you can get those values to be the same. And that's just, again, just kind of the way that you're interacting with the interface here. But as long as the values are the same, it's fine. Anyway, so let's go ahead and just go ahead and run this. See if they both go in the same direction after the collision. Yep, almost. All right. So one thing is that this one here is going so high. See, let's make it slightly, so the center masses are still unaligned, but now instead of them almost missing each other, they're kind of coming in. Okay, there we go. Definitely a state where they're both going off to the left after the collision. Okay, and then you don't want it to hit the wall if you're going to collect and you need to collect your final data. So in that case, just to show you, after the collision, I would want to have stopped and collect data before either of them hit the walls. And last thing then is you want them both to continue to the left after the collision. Well, let's go ahead and reset. What are we going to change in that case? Well, let's just make red really massive. All right, see if that works. Almost. Let's make green less massive. Okay. Let's reset again. Okay, there we go. That works. Okay, so you get the idea. Those are the 3 final states, and you want those 3 final states for each of the 6 types of collision. So if I talked about collision 1 as an example, I'm not going to show the final states for each of them because that idea holds true. But let's just make sure that you are clear on what the other 6 initial states are. Because to be clear on the wording here, the 6 experimental procedures are all about initial conditions. The analysis question, where it asks to make sure that you chose initial conditions so you have 3 final states, well, those are final states. Okay, so it's a combination of 6 initial conditions and 3 final states for a total of 18 data sets, to say it again. All right, but anyway, let's look at number 2. We can go back here, reset things. So what's different this time? So here it says, so align the initial velocity vectors so they each face each other. But look, the only difference is elasticity is adjusted. That's the only thing that's changed. And we're adjusting elasticity until k final is half of k initial. So let's go ahead and set things up. Let's run it. So let's look at, I'm going to adjust one of these vectors to be slightly shorter and get it to be the same value. I just want it's nice to have your kinetic energy be like a nice clean number. Let's see if we can get it. Something that divides by 2 easily. And it's fine. And the thing, don't worry about your kinetic energy too much. It doesn't have to be exact. So here, I'll show an example where it's not. So here we have our kinetic energy, and it's got a value of 1.48. Our velocities are exactly lined up, as you can see, so that's good. So that's our initial kinetic energy. If we run it at 100% elasticity, notice what happens. After the collision, it stays at 1.48. That's the point of 100% elasticity. But if I turn it down to 50, I won't get 50% of the energy, because elasticity and energy are not the same thing. So if I run it, see, it's less than half now. So it went, well, it's actually, let's see, is it less? Because it went 1.5. Actually, it's greater than half. Right? See, it's 0.8, whereas 0.75 approximately would be half. Is it close? It's pretty close. But let's turn my elasticity down a tad more. And the type of collision really matters, right? So different collisions of different mass, velocity, and angle combinations, the elasticity will change. And that's why you don't have to get it perfect. You just have to make sure it's around 50%. So here we go. That's better. I'd say that is acceptable. That is close enough to 50%, because ultimately you're just going to be taking the data and comparing it and showing that the math checks out, thereby getting practice with the numbers. So it doesn't matter that this isn't exactly 0.75, 5 or something. We can't even see the 3 significant figures either. Okay, I guess it would be 0.74 would be exactly what we're looking for. Okay, all right, this sounds right. So anyway, but moving on, the arithmetic aside, that's what you're going to do for this one. Otherwise, procedure 2 is identical to procedure 1. So you do the same thing. You look for 3 final states and definitely record that final kinetic energy and calculate it based on the velocities and masses after the collision. Okay, so that's 2. What about 3? What's different in 3? Okay, so let's reset things. So this time, and notice there's more wording here. It says align the initial velocity vectors so they face each other along the x-axis but are slightly out of alignment. Okay, and we're going to go back to 100% elasticity. Okay, we'll change that in a minute. And then we're going to say make sure they're not so aligned as to not collide, and align the center mass of the system so that it does align with the geometric centers of the ball. So this is different. Now we're actually aligning the center mass, but offsetting the velocities. So I'm going to drag 1 until it has the same y position as 2. So I want it to be negative 0.196, just like 2. Let's see if we can get it. Okay. See, it wouldn't land on 0.196, but then I should be able to get them to. This is final point where they'll be the exact same value. This time it is giving me an issue. It could be the size. Let's try making it a little bit smaller. See if that will line up. It's giving me different values, but still not the same ones. No, you can get close enough. 24 and 23, yeah. So this is acceptable. When it's giving you trouble like that and it won't line up, that will happen occasionally. Just get within that last decimal point and make sure it's no more than a 0.005 difference. Okay, that's totally acceptable for this one. But a lot of times you will be able to get them to line up. Okay, so as I was saying, only thing I'm going to change now is the velocity vector. So I'm just going to make one so that they're not head-on anymore. That's the difference, right? They're not actually going to be, the velocity vectors will not be anti-parallel to each other now. That's all it's changed, okay? Back to the 100% elasticity. Let's run it, right? And you just look for the 3 different final types of states based on their velocities and masses. In other words, their initial momentums. Okay, so let's reset it. Look at number 4. All right, so this one, what's going on? Well, okay, so now it's exactly the same as the last one, still 100% elasticity, but we're just going to pull one up so that their centers don't align. So for example, I just pull 2 up a bit and run it. Okay, so basically everything's kind of out of alignment there. Neither their center of masses nor their velocities are lined up. Okay, all right, looks good. All right, and that would be a problematic one because that one's kind of going straight down. So you could just adjust things to make one of them go in a clearly defined direction. Okay, that is, has a horizontal component. That is right. Two left. So the last two are just like 3 and 4, but with half energy. So adjusting the elasticity. All right, so we could do 6 first because we're already set up for it. Not aligned centers, not aligned velocities, and the only thing we do is just drag down the elasticity. So kind of a good starting point is 50. See what that gives us. So let's go to 51. See if we get something that's half of 1.14, which would be let's see, it would be 0.55 or no, 0.57. So let's see if we get 0.57. Yeah, pretty close. We could see if we go up a bit. Even better. That's perfect. 0.56 is totally acceptable. So that would be a good elasticity choice for getting half kinetic energy, and that would be number 6, by the way, procedure 6. Okay, because we're already, like I said, we're already set up for it. But let me show you 5 next. I know all the examples I've been doing, elasticity's kind of been ending up being close to 50% to give us 50% energy. That again, that's not always the case, right? So don't necessarily expect that, depending on the masses you use. All right, the last one is with their velocities aligned, but make sure they're not so angled. Oh yeah, so actually this is with their center masses aligned, but their velocities offset. So 5 is basically just like 3, but with elasticity reduced. Okay, so I would take this one and line up the velocity again. Or actually I would unalign the velocity, so maybe something like that, like it was already. And then I'd try to get them at the same location. So we'll do 17. I know this was giving us trouble before. I think it still is. It really doesn't always do it. Oh well, we'll just stick with the within 3 in this case, which is certainly within the 5 of my my suggestion there. Okay. All right, so that's close enough, and then we just run it. See if we get a number that is going to be about half of 1.23. So we're looking for maybe 0.61. Let's see. Perfect. Okay. So there we go. Our sticking with 53% elasticity worked well. All right. So that would be procedure 5. Right. Notice how their centers were aligned, or darn near close aligned, but their velocities were not anti-parallel, and the elasticity was not 100%. All right. Okay, and that's it. That's the idea, and you're just going to complete the kind of the equations and draw the figures for each one of those 18 different types of collisions. Because ultimately, you get the different final states. You need 18 different initial states. Okay, hopefully that all makes sense, and you can answer the second analysis question, and you kind of have some fun really seeing how collisions work, because that's a neat thing about doing this so many times, is you really get some intuition for it. Okay, well, thank you so much for watching this directional video.